When people hear the word expansion, they often picture galaxies flying outward into empty space. That image is close enough to start, but it misses the main point. In modern cosmology, expansion is not matter moving through space. It is space itself changing its scale with time. Gravity is the actor that decides how that change unfolds. It can slow the expansion, it can shape where matter gathers, and on the largest scales, it seems to share the stage with something that pushes in the opposite direction. I want to build this from the ground up, using what we actually measure. The first key idea is that gravity in Einstein's general relativity is not a force in the usual sense. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. On everyday scales, that reduces to the familiar pull of Newton. On cosmic scales, the curvature of spacetime controls the overall expansion history of the universe. In a universe that is uniform on average, the expansion is described by a single number that changes with time, called the scale factor. The rate of change is the Hubble parameter. What determines how that rate evolves is the total energy budget: normal matter, radiation, dark matter, and dark energy. Each component dilutes differently as the universe expands. Radiation thins out fast because its energy also redshifts. Matter thins out more slowly. Dark energy, at least in the simplest model, does not dilute at all. This is where gravity's role becomes subtle. In general relativity, not only energy density, but also pressure gravitates. For normal matter, the pressure is small compared to its energy density, so gravity is attractive. For radiation, the pressure is positive and contributes to gravity as well. But for dark energy, the pressure is negative. In the simplest case, a cosmological constant, the pressure is exactly the negative of its energy density. That combination makes gravity act repulsively on the scale of the whole universe. It does not mean objects repel each other locally. It means the expansion of space accelerates because the stress energy of dark energy curves spacetime in that particular way. How do we know expansion is accelerating? The cleanest evidence comes from type 1a supernovae. These are exploding white dwarfs that reach a predictable peak brightness after calibration. By comparing how bright they appear to how far away they are, we infer distances. We also measure their redshifts, which tell us how much the universe has expanded since the light was emitted. In the late 1990s, supernova surveys found that distant supernovae were dimmer than expected in a universe that is slowing down. The best fit was an expansion that has been speeding up for the last several billion years. Supernovae are not the only pillar. The cosmic microwave background gives us a snapshot of the universe when it was about 38,000 years old. The tiny temperature variations across the sky encode the geometry and contents of the universe. In particular, the angular scale of the first acoustic peak tells us the spatial curvature is very close to zero, meaning the universe is very nearly flat. But a flat universe with the observed amount of matter, both normal and dark, does not match the supernova distance relation unless you add a dark energy-like component. Baryon acoustic oscillations, a standard ruler imprinted in the distribution of galaxies, then connect the early universe to the late universe and reinforce the same picture. Independent methods, different systematics, one consistent story. The universe is expanding, and the expansion is accelerating. Now, how I want to connect expansion to structure, because gravity does more than set a global rate. It also amplifies tiny initial irregularities into the cosmic web of galaxies and clusters we see today. The early universe was extremely smooth, with density variations at the level of about 1 part in 100,000. We see those variations directly in the cosmic microwave background. Under gravity, slightly denser regions attract more matter, becoming denser still. Slightly underdense regions lose matter and become emptier. This is gravitational instability. If the universe were only normal matter and radiation, This growth would be too slow to form the observed structure by today. The reason is that early on, normal matter was tightly coupled to radiation. Photons scattered off electrons, and that pressure resisted collapse. Dark matter changes the game because it does not interact with light in the same way. It can begin clumping earlier, creating gravitational wells. After atoms formed and the universe became transparent, normal matter could fall into those wells. That is why dark matter is central to large-scale structure. It is the scaffolding. We infer dark matter from several lines of evidence. Galaxy rotation curves show stars orbiting too fast to be held by visible matter alone. Clusters of galaxies have too much gravitational binding compared to their luminous mass. Gravitational lensing lets us map mass directly because mass bends light. In systems like the bullet cluster, the hot gas that contains most of the normal matter is separated from the lensing mass after a collision. That separation is hard to explain without a dominant collisionless component, which fits dark matter. On the largest scales, the pattern of galaxy clustering and the lensing of the cosmic microwave background also require dark matter to match observations. So we have a universe where gravity pulls matter together, and dark matter provides most of the pulling mass, and yet the expansion is accelerating due to dark energy. These two tendencies compete. Early on, matter dominated. Gravity slowed the expansion, and structure grew efficiently. As the universe expanded and matter diluted, dark energy became relatively more important. Around a redshift of about 0.7, give or take depending on parameters, the expansion switched from decelerating to accelerating. From that point on, the growth of large-scale structure began to slow. Galaxies still form, clusters still merge, but the rate at which new large structures assemble is reduced because the background expansion is stretching space faster. There is a useful thought experiment here. Imagine a small overdense region in an expanding universe. If it is dense enough, its self-gravity can overcome the expansion locally. It can stop expanding, turn around, and collapse into a bound object. This is how halos form. But if the expansion accelerates strongly, it becomes harder for large regions to ever reach that turnaround. In the far future of an accelerating universe, there is a scale beyond which structures will never become gravitationally bound. The cosmic web effectively freezes in comoving coordinates. Bound systems remain bound, but unbound regions drift apart faster and faster in terms of physical distance. This brings me to spacetime itself. In general relativity, the expansion is encoded in the metric, the rule that tells you how to measure distances and times. Galaxies at rest with respect to the expansion are not moving through space. They are following geodesics in an expanding spacetime. Light traveling through that spacetime is stretched, which is why distant galaxies are redshifted and why the cosmic microwave background has cooled from thousands of degrees to 2.7 Kelvin today. This is not a Doppler shift from motion through a static space. It is a cosmological redshift from the stretching of wavelengths as the scale factor grows. We test this framework constantly. We check that time dilation in supernova light curves matches the factor of 1 plus redshift it does. We check that the surface brightness of galaxies dims with redshift in the way expansion predicts. It does within observational limits and astrophysical evolution. We compare different distance measures, like luminosity distance and angular diameter distance, and we find consistency with an expanding metric. These are not just philosophical preferences, they are quantitative checks on the geometry of spacetime. Now for the most important unknown. What is dark energy? In the standard model of cosmology called lambda CDM, dark energy is a cosmological constant, lambda. It is mathematically simple and it fits the data well, but physically it is puzzling. Quantum field theory suggests that empty space should have a vacuum energy, yet naive calculations give a value wildly larger than what we infer from cosmic acceleration. That mismatch is the cosmological constant problem. It is not a small detail. It is one of the biggest gaps between our best theory of the very small and our best theory of the very large. Because of that, we keep testing whether dark energy is truly constant. We describe it with an equation of state parameter, W, which is the ratio of pressure to energy density. A cosmological constant has W equal to -1. If W differs from -1, or changes with time, then dark energy might be a dynamical field rather than a constant property of spacetime. Current observations are consistent with W equal to -1 with uncertainties. Future surveys aim to tighten those uncertainties using supernovae, baryon acoustic oscillations, weak lensing, and the growth rate of structure. Another uncertainty sits next to this. We assume general relativity is correct on cosmic scales. It passes every test in the solar system and in many astrophysical settings. But cosmic acceleration could, in principle, reflect a modification of gravity rather than a new energy component. Many modified gravity models exist, but they must reproduce the successes of general relativity while also matching the detailed pattern of structure growth and lensing. So far, lambda CDM with general relativity remains the simplest model that fits the full range of data. Still, the door is not closed. The growth of structure is a key discriminator because modified gravity often changes how potentials evolve and how light and matter respond. With this in mind, what does gravity say about the fate of the universe? If dark energy is a cosmological constant, the expansion approaches an exponential form. Distant galaxies outside our local group will eventually cross a horizon where their light can no longer reach us. Locally bound structures remain intact because their self-gravity dominates over the expansion.